All right, everyone. How are you guys doing today?
All right.
All right. Any? Okay. We're nearing the end of the semester. I probably say that about once per day. I realize I repeat myself a lot these days. Not a problem. As we approach the end of the semester, if I haven't said it yet, in case I don't get the chance or don't remember to say it again, it's obviously been a very strange semester, and under better circumstances, I'd like to have you guys in a more normal class, but it was still nice having you guys this semester, and it has been fun, and I hope the next one will continue to be good and effective and pleasant. Try to close the semester well, and I've been glad to be your professor, even if it's not the semester you probably would have liked optimally. But thank you all for making it as good as it could be, given all the insanity. I hope you're all doing well. Hope you're all getting plenty of rest. I'm really projecting when I say that, because I'm very sleepy. I'm not sleeping very well. So get plenty of rest and plenty of water, especially during exam week. Any questions, comments, concerns, or needs before we move on today? Okay. Well, I believe last time we had at least, yes, we talked about Ohm's law. And I wanted to at least get to this point because Ohm's law is important to the lab this week if you have not done it yet. So as a brief refresher, if you are examining a circuit and all of our electronic devices contain and/or are themselves circuits, the three things you need to actually make electricity flow through a circuit are voltage. This is the pressure that drives the current through the circuit. That will actually make the current itself flow. So this is the current. And then R, the resistor, is whatever you're pushing the current through. This is whatever you are powering in the circuit. So when you plug your phone into the wall, your phone is a resistor in the circuit of the wall. And the wall's voltage pushes current through your phone. And that's what every piece of this particular formula means. This is important. If you have not had lab yet this week, keep this in the front of your brain. Now, before we shift from electricity and start talking about waves, and I do want to get into waves for the bulk of today, simply because I really like talking about it, and even if you never ever think about the math behind electricity again, you are definitely going to interact with waves, considering everything you see or hear is a wave. Before we end off on electricity, I want to talk a little bit about what electricity isn't. And electricity isn't a magnet. Magnetic fields are similar to electric fields. Protons and electrons give off electric fields, like how mass gives off a gravitational field. And when those fields interact, they create force. Magnetic fields are different from electric fields. Protons and electrons give off electric fields because they are charged. Magnets give off magnetic fields. Although we're really not sure why, magnets is still one of the funnier mysteries within physics, because we know that they work. We know a lot of math and measurements for being able to calculate what a magnet's strength is and what it will do. But in a lot of cases, we still don't know why magnets work, like on a molecular level. For electricity, we know about the charges in protons and electrons, but there's no particle that creates magnets. So these are similar to electric fields. Most magnets have a north pole and a south pole, and the magnetic field goes from north to south, like how electric fields go from positive to negative. But it's kind of a weird toss-up as to what exactly naturally has a magnetic field. Iron reacts to magnetic fields, but iron doesn't produce one by itself. The Earth has a magnetic field, even though we're not entirely certain why whatever's happening in the center of the Earth makes that magnetic field. But it exists, and it's good that it exists. At a fundamental level, the reason why the electric forces and the magnetic forces are similar is because they are two halves of the same thing. We've mentioned how gravity and the electric forces are very similar because they are two of the four fundamental forces that literally hold the universe together. There's lots of important constants in physics. These four are just the literal forces that are Newtons that hold the universe together. Gravity, the electromagnetic forces, weak nuclear and strong nuclear. Electricity and magnetism are literally the two halves of the electromagnetic force. And even though they are related, they are still distinct. Brief list of their distinctions and similarities. You can measure electric fields and magnetic fields separately, and what they will affect is different. Iron by itself is not affected by an electric field, but it is affected by a magnetic field. Earth has a magnetic field, but it does not naturally have an electric field. There's a lot of weirdness as to what they're similar in, what regards in which they're similar and what regards in which they are different. The main thing I want you guys to remember is that electricity and magnetism are not the same thing. Our circuits do not run on magnets, although oftentimes there are magnets in circuits, which just leads to confusion. And some of the specific benefits and uses of a magnetic field over an electric field. I've already mentioned that planet Earth has a magnetic field. This little tiny blue dot right there is the Earth, and that's the Sun. I think their sizes are pretty close to scale here, but the distance between them is not. The Sun is constantly blasting radiation at planet Earth, and our magnetic field helps to shield us from a lot of it. It's literally a force field that stops a lot of the radiation from the Sun from actually striking the surface of the planet, which is good. Currently, the dose of radiation we're getting is what we need, and without that magnetic field, we'd be getting way too much, and everything would be on fire forever. Radioactive and on fire, which is a bad combo. Lots of other commercial uses for magnets. They're very commonly also found in both generators and in motors. So any electric, that means like your phone, the vibrate function on your phone is caused by a little electric motor that a little magnet makes a little thing spin around, and that wobbling is what makes your phone shake. All electric motors are similar, and they use a magnet as a part of a circuit. So, again, related but distinct. And I would like to use that to sort of segue us into our next category, because we do need to talk a bit about waves. And there's two specific kinds of waves that we're going to be looking at. And the nature of one of them explains why Earth's magnetic field can block waves. specifically the radiation from the sun. So, before we get into that, any questions at all about anything we talked about so far today or last time? Okay, so switching gears a little bit. Now this is probably the first thing most people think of when you say the word wave, and I do not fault them for that. But as we're going to discuss, what you see here, the water you actually see, isn't actually the wave itself. A wave, as defined by physics, is not an amount of water on the ocean. A wave, as defined by physics, is traveling energy. Whenever you create a wave of any type, you are sending energy from one place to another. Say, for instance, I hope you all had a slinky, or at least got to play with a slinky when you were kids. No reason you can't now. I usually have one as a desk toy. When you, say, pull the slinky taut and have it stretched out like several feet, and you just sort of shift your hand to make one end of it shake, the vibration travels from one end to the other, and usually it'll echo back and forth a few times. Does this sound familiar? So what you're doing there is you are creating a wave, and what actually travels from one hand to the other isn't the slinky, because the coils you're holding don't leave your hand. These coils don't go over here. The actual wave, the part that travels, is just energy. You put energy into the slinky, the energy travels down and makes the slinky shake, and then it'll keep bouncing back and forth. Waves are just traveling energy. Now, oops. Waves can travel through objects, and they make the objects shake when they do that, which gives the appearance of, that lets you actually see the wave, because like we've talked about with energy before, we cannot see energy. We can only see what energy does. So when you see a wave, you're seeing the thing, the object that the wave is moving through, and the wave is making that object move as it does so. Specifically with like an ocean wave. Usually the wind is the source for those. Wind puts energy into the water, and the energy, as the energy moves through the water, it'll make the water shake in whatever spot the energy is in, and the energy keeps going. Meanwhile, the ocean that it passed through does not keep rushing towards the shore. If the water was traveling, the entire ocean would come up every single time a new wave came in. So it's just the energy that, like the ripple you see is the energy in a different spot, and the energy is what's moving. And there's two main types of waves we're going to be looking at. The first type is the kind we've been already discussing here. Mechanical waves are energy traveling through some physical medium, some object. These are the kinds that you can actually see because something is physically moving. Again, like with an ocean wave, you see the ocean moving. So the ocean is the medium that the wave's energy travels through. Earthquakes are also created by waves, and the medium that that wave travels through is the Earth itself. When earthquakes happen, some seismic activity beneath the ground causes the tectonic plate to shake. The energy travels through the literal Earth and makes it shake as it just spreads out. That said, not everyone lives at the beach, and hopefully not everyone goes through an earthquake. The type of mechanical wave that people are definitely most often interacting with is a sound wave. All mechanical waves need a physical medium for them to be able to travel through. What is the medium for sound waves? Air. Without air, sound doesn't exist. You can only hear me right now because there's air between you and I for my sound waves to travel through to reach your ear. Which is why in movies or on TV or in science documentaries, you might have heard the statement that sound doesn't travel through the vacuum of space. If you were just in a spacesuit, freely floating through space, it doesn't matter what's going on around you, you won't be able to hear it. If an explosion happened nearby, you'd see it, but you wouldn't hear it, because there's no air for the sound to travel through, which is kind of frustrating when you're watching stuff like Star Wars, and every time a ship blows up, there is an explosion sound. Wouldn't actually happen that way, but the filmmakers have to put it in so that things look and sound right to the audience. Excuse me. And sound is another good example of how it's only the energy traveling and not the medium. If the air traveled with my sound wave, every time I spoke, you guys would be hit by wind. Because my vocal cords make the air shake. The energy travels through the air to get to your ear, but it doesn't bring the air with it. If it did, again, I'd be making gale force winds every single time I open my mouth. So those are all mechanical waves, and they require a physical medium. There's a different type of wave that doesn't, though. These are the types that most people think of when they think waves, but there's something else, another type, that has very distinctive wave properties, but does not require a physical medium. And those are electromagnetic waves. These waves require no medium. They don't need an object to travel through. This is the type of wave that can travel through space. And the most famous example of this type is light. Light is an electromagnetic wave. It is, in its purest form, traveling energy. All waves are traveling energy. These ones specifically is energy by itself without requiring a medium that can just fly on its own through the vacuum space. And we call it an electromagnetic wave because if you look very closely at what it actually is, it is an electric field and a magnetic field traveling together in the same direction. Light is very weird when you start analyzing what it actually is on a fundamental level, but the main thing I want you to remember is because it is electromagnetic, it can be deflected by Earth's magnetic field, which is why all the radiation from space is deflected by our field and why we aren't on fire right now. So, main points: light is an EM wave. It's weird on a fundamental level. It can travel through space. It can be deflected by a magnetic field. Does not require a physical medium. It can travel through one, but it doesn't need to. These are the two main types of waves. Every wave is one of these two things. And we're going to take a second to look at sort of the structure of a wave, and then looking at each type specifically to analyze its main properties, the things you need to most know about it. I'm going to put this slide up, but I actually need to run to the restroom real quick, so what I recommend you guys do is take this time to take a quick break and/or copy some of this information down. And I'll be right back. Sorry about this. Okay. So, these are the things that sort of make up the body of a wave. Granted, the wave itself is just traveling energy, but as that energy travels, it does create a specific pattern in whatever it is traveling through. If you've ever gone into your calculator and graphed a sine function, like either just because or because you're doing it in geometry class, and if you ever went in and graphed sine of x, your graph probably created a shape something like this. And most waves, if you can analyze the specific structure that the medium the wave is traveling through takes, will take on a shape similar to this, as the medium oscillates up and down as the wave travels through it. This is sort of the most classical wave shape that most people would look at and call a wave. And this wave form is made up of some specific things. The wave has an amplitude, which basically just refers to its size. If you were on a boat and a 10-foot tidal wave passed you, the amplitude of that wave would be 10 feet. It's just physically how tall is it. It is worth noting, though, that that height is from the base state, because waves can and will oscillate up and down from this particular spot. It's not super obvious with an ocean wave, but there are high points and there are low points beneath what the water's surface would normally be. And the amplitude is the distance from that base state to the very bottom or to the very top. So it's just a measure of physical size. All waves also have a frequency. This basically tells you how many waves are going to pass you each second. Frequency is measured in a unit called hertz. It's spelled H-E-R-T-Z, like it's a car shop. There's a store called Hertz. But it is abbreviated to HZ. So F is the variable for frequency, HZ, hertz is the unit. And you've probably heard the unit of hertz before. It specifically refers to frequency. And for the waves that you most commonly interact with, those being sound and light, the frequency is going to determine, for sound, what pitch you hear. You can have very low frequencies that correspond to very low sounds, or you can have very high frequencies that correspond to very high sounds. So, for sound, frequency determines pitch. For light, frequency determines color. So every different color of light is a different frequency of wave. And that just tells you how many times the wave is going to shake in a fixed amount of time. The inverse of frequency is the period of a wave. It basically tells you the same thing. Frequency at a technical level is the number of times the wave passes every second. Period is the number of seconds it takes one wave to pass. So they're just inverses of one another. And then wavelength. This is a physical length. So it is measured in meters. You can measure it with a meter stick. The variable for wavelength is this, I believe it's a lowercase lambda. It's kind of like an upside down Y. This is the physical length of the wave. If you could freeze time and you had an ocean wave just in front of you, you could take a tape measure, measure how long it is. That's its wavelength. It is exactly what it says in the tin. You do need to define the length of one wave, and a whole wave is from a specific point on the waveform to the next iteration of that point on the waveform. So if you're measuring the length from the top, like the very top of a wave, you need to measure the distance to the next top of the wave. And so you take that physical tape measure, especially from here to here, that is the length of this wave. You could also measure from falling to falling, you can measure from bottom to bottom, etc. As long as you are measuring to the next iteration of that spot. So specifically, the wavelength screen right now, this is 5.2 centimeters, that's from top to bottom. We need to go from top to top, so the wavelength of this wave would be 10.4 centimeters. Now the two from this that I want you to focus or remember the most are wavelength and frequency, because they best define the specifics of what color you are seeing or what sound you are hearing. Every single different sound, every single different color corresponds to a different frequency, and each of those frequencies has a corresponding wavelength. That's important because for any specific wave, when you multiply its frequency by its wavelength, that will tell you the wave's velocity. So these are the four things that make up the structure of a wave, but every wave in addition also has a velocity that it is moving at, because a wave is traveling energy. If it is traveling, it needs to have a speed at which it is traveling. You can find that velocity by, again, taking the frequency and wavelength of the wave in question and multiplying them together. And conveniently, all waves of a specific type have the same velocity. All sound waves traveling through air travel at the same speed. I've got it written over here. The speed of sound in air is 343 meters per second. All sound waves in air travel at this speed, which is why it doesn't matter what type of sound I'm making, it will still take the same amount of time for it to get to your ears. All sound waves have the same velocity, which means that if you change the frequency of sound, the wavelength has to change accordingly so that they still multiply together to make the same velocity. Every single frequency of sound has its own matching, very specific wavelength, such that they have to multiply together to create the same velocity. Now, light also has its own specific speed. The speed of light is 3 times 10 to the 8th meters per second, which is 10,000 times faster, approximately. So light is literally the fastest thing that we know of in the universe, that we can observe directly. Granted, you can't see the light itself, but you can see what the light does and what it bounces off of. And we have measured, or at least calculated, that this is its top speed. And all light and all every form of electromagnetic radiation is going to travel at this speed. Since light is so much faster than sound, you will always see something before you hear it, which is most obvious with thunder. In a lightning storm, I presume there's been a point in your life where you probably saw a bolt of lightning, but then you didn't hear the thunder for a second or two later. It's entirely due to the difference in these speeds. The light will reach your eye much faster than the sound will. And because of this difference, you can actually measure, like if you were recording the time between seeing the bolt and hearing the thunder, if you measure that time, you can use it to figure out how far away the lightning strike was. So, all waves have a specific speed. Those are the two wave speeds that will be best to remember. These constants will be made available to you. They are constants, so they're not going to be hidden from you. We treat these as known values if speed of sound or speed of light comes up in a question. Any questions so far? So, let's look at each of the two main types of waves. Okay, we're going to look at sound and light in specific now. Just look at the main features of each that you should be familiar with. Sound is, again, a mechanical wave. It means it has to travel through a medium. It's a longitudinal wave, which is a different classification. It means that when I make the air shake with my voice, the air shakes back and forth instead of up and down. So sound doesn't actually form this shape, but you can't see it anyway. We've studied the way the air moves, and it looks a little more like a slinky compressing than it does a normal ocean wave. But the main thing to take away from this is sound needs a physical medium, but it doesn't necessarily need to travel through air. We hear it through air because our ears are built for that, but it can travel through other things. What we have here is a list of the speeds of sound through lots of different materials. If you've ever been underwater, you've probably heard sound travel through water. Granted, the human ear wasn't built for that, so it's always going to sound funny, but you can hear something. And if we look at the wave speeds in these different mediums, we have different temperature air, and the temperature of the air affects the wave speed as well. So that's something to be aware of. These are the speeds of sound in air. Oxygen is a part of air, so this is that wave speed. Hydrogen is really fast, but compare these to the speed of sound in liquids. Barring the exception of hydrogen, all of these liquid speeds are faster than most of these gas speeds. And then, the speed of sound in solids, for the most part, tends to be even faster. So the speed of sound through anything tends to depend on the density of that medium. Sound is fastest in solids, then liquids, then gas. So really the thing we hear sound through most often is kind of the most inefficient medium that sound can travel through, but humans can't breathe underwater, and you can't exist inside of a solid object, so we just make do. But because of this difference, this is one reason why earthquakes are so dangerous. Waves just travel faster through solids, which includes the ground. So an earthquake can go from its epicenter to halfway across the continent in minutes. But additionally, there's a trick you can do because of this fact. It doesn't show up in movies much these days, but there's a trick that I have seen in movies and TVs before, where someone would physically get down on the ground and put their ear to the dirt. And in doing so, since your ear is the part of your body most sensitive to this type of wave, you can hear, or at least feel, a train coming, or a stampede coming, or a car coming faster than you would and better than you would through the air if you stick your ear to the ground. Because the waves will get to your ear faster through the dirt than they will through the air. Specifically, if you put your ear to a train track, you can feel like there's a train coming, but I'm not recommending you put your head near your train rails. So, official disclaimer, don't put your head on train rails. Now, you're not going to need to remember any of these. The only speed of sound that you're probably ever going to need is this one, since you will only ever hear sound through air, or maybe water. If you need the speed of sound in water, it will be provided to you. This is the constant that will do you best to remember, but this will also be given to you. To use this very quickly, specifically referring to the lightning example, we're going to assume, again, the speed of sound in air is 343 seconds, so 343 meters per second. And it takes, let's say that you see a lightning bolt and you only hear thunder 6.4 seconds afterwards. What is the old original first formula for velocity that we talked about in the beginning of class?
Mass over acceleration.
Very good. Delta D over delta T. So, we know speed of sound. We want to know how far it traveled. We know 6.4 seconds. So delta D will be 343 times 6.4, which will be some number probably around 2,000.
2,195.2.
Thank you. Say it one more time.
2,195.2.
Thank you. Which is a whole lot of meters. I'm actually surprised. If this were to happen in real life, that would be very faint thunder. You wouldn't hear it very loudly. But this is a useful trick that humans often employed before we had meteorologists to tell us where the storm is. And in general, you can do this with all wave speeds. This is still the formula for velocity. You can still do V equals V over T. Now, additionally with sound, this is something really cool that I want to mention to you, even though it's not in the notes. It's just really cool to me. The pitch of sound, like the actual, whether or not it's a high note or a low note, depends on its frequency. And humans can only hear very specific frequencies of sound. Sound waves can be anywhere from 0 to infinity in frequency, but humans can only hear sounds in this range. If a sound is lower than 20 hertz, your ears can't pick up on it. It's a low frequency with a very long wavelength. You're more likely to feel it physically impacting your body than you are to hear it. Meanwhile, sound that is this high, your eardrums just physically are not equipped to deal with it, so you just don't. What's worth noting is that the hearing range of dogs is about 40 hertz to 40,000 hertz, which is why there are sounds like dog whistles that dogs can hear and we can't. But I guess there's also a few sounds between 20 and 40 that we can hear that they can't. What's interesting about this, though, is as you age, if this is the upper limit of human hearing, as you age, this number gets smaller. When you are born, your ears are as pristine and effective as they will ever be. Every second you're alive after that, your hearing is constantly getting worse, as just the cells in your eardrum naturally age and fall apart. By the time you're me, if you are, late 20s and don't necessarily avoid loud music funneled directly into your ears by a headset, your hearing range probably drops to about 16,000 hertz. And as you get even older, I think by the time you reach your 80s, it'll probably drop even further, like maybe 12,000 or 10,000 hertz. Which means there are sounds you guys can hear that I can't. Granted, they're really high-pitched, whiny ones that you wouldn't want to hear anyway, but you can. Take care of your ears, because age and also damage can reduce this number. There's also sound tests you can take to see what your upper limit is. I'd play one for you, but the speakers are busted, and they're usually pretty long, and the sounds are really, really uncomfortable. It's just a pure whiny pitch. So if you're interested, I recommend you do it on your own time with headphones on so that your roommates aren't bothered by the constant whining. Now, sound is mechanical. It doesn't need a medium. But light does because it is electromagnetic. Sorry, wait. Sound needs a medium, light does not. Yes, that. And This is not something that you will ever see because you can't actually see light itself. Whenever you see something, what you're seeing is light that bounced off of an object and then hit your eye. You can't actually, an individual light wave is called a photon, and the human eye cannot track individual photons. But if you could, it would look something like this. It's an electromagnetic wave because it's made of an electric field and a magnetic field traveling together in the same direction. Which again is just why a magnetic field like Earth's can deflect up. And light is really, really